So what I'm going to do here is show you a little bit, just a notebook here, and then I'm going to show you a little bit like what you can do. And then I showed you last time how to make a Kaggle notebook, Kaggle kernel directly on Kaggle, but we can also work on Jupyter Notebook, and I'll show you all how to like upload it from there. So I just wanted to go through some stuff that maybe we haven't seen directly, and I think it's kind of useful to just kind of like walk through this. Most of this is actually really heavily inspired by the data science, the Python data science handbook. Just kind of know is that if you probably look into like the feature engineering section and the linear regression section, you'll probably see very similar stuff. I'm just kind of distilling it down to make it a little bit more focused on like what we're looking at. Okay, so you can see here, like the first thing I want to do, like I'm going to do an example linear regression here. I have my different imports and stuff like this. We can talk maybe a little bit more in the future, like, how do you know what things to import? But one thing strategy you can do, because you kind of edit your notebooks, is I usually put all my imports all at the top. When I'm teaching stuff, sometimes I'll put imports directly when I'm referencing something, just because I want to really focus on like, hey, like this is like how you would, use this tool. For example, I think I show you guys in this notebook Polynomial Features. I'll do the import right there because I want to emphasize this is how you do polynomial features. But when you do your notebook, you probably will put all your imports at the top, and that way someone can look at your notebook and very quickly understand what things they need for them to run this notebook. Okay, so got this stuff here. Hopefully this all looks pretty familiar to you all. Pandas, NumPy, Matplotlib, Seaborn. This guy right here, which is probably like what is this kind of thing you put at top. I sometimes would like to put flags, especially when I make a final like notebook, where I basically put things where like I would like to print out details if I feel that it's really necessary, like when I'm kind of playing around with it. But like it's like, oh, when I run my whole notebook, I don't want to show all this extra details. I'll put this little flag here so that way I can just say if this is true, and most of the time it'll be false, it won't print out those details. In this case, since I'm showing you all, live here and just string, I'm going to set this to true. Okay. So this is just a little extra thing that I do. You won't see it all the time. All right, so first thing I'm going to do is just basically get some random points. I'm going to 100 data points. And in this case, I'm creating data points and I kind of want this extra structure. So I'm just basically just getting from -3 to 10, and then getting, in this case, 100 data points. And basically I'm just using this equation, which you can see is a quadratic equation, and I'm just adding some extra noise to it. So that's what this random endpoints here. So just kind of know like this is how you can kind of generate some extra data that's like little noisy data. In reality, you would not be doing this. You would probably import your CSV or whatever data. Okay, but just to show you what that looks like, this is a simple one feature, one target. But of course, you can probably figure out how to kind of expand this out to multiple features, multiple linear regression. Okay, so let's actually do this. So one thing to kind of note is that since I am using one feature, for the X, which is going to be our feature array, I have to reshape this X array. And so the reason why I'm going to show you a little bit here, since I have the print detail, is that, oops, there we go, is that X by itself is basically in a different shape than what most linear regression machine learning models packages are expecting. So we expect basically is that each row in X is going to be one data point, and then each column is going to be a feature of that data point. So what I did here when I reshape it, and this is a little kind of trick, this -1, 1, basically this ends up making it so that you have, I'll show you what this looks like exactly. But basically, instead of starting off with a NumPy array with like 100 elements in a row, so it's like one row but 100 different elements, it reshapes it where there is 100 elements but each has one row. It's a subtle difference, but I'll show you what that looks like. So after reshaping, what this looks like is it has a shape of 100, 1, okay, which basically can translate as 100 rows with one column each. Okay, and you can see when I actually display it, you can see here like, oh, this is the one data point and it's only one column. If I had two columns, this would be one data point and then it'd be like a little array, comma, with another value in there. Okay, but since there's only one, that's what it looks like. Now, if I scroll down a little bit, so you see, this is why I don't like to print everything. You can see here, it's before the reshaping that X, right, is actually just 100, which is a little bit different from 100, 1. And that's because if you look at the structure now, this basically is just what we like a one-dimensional array, which is basically just a row of a bunch of data. But you can kind of imagine that's not quite what we want, right? We want the rows to represent each new data point for the features. So that's why I have to do that reshape. For the record, you don't have to reshape when you have multiple features, because it'll automatically come out, where we have each data point is on a single row with columns. But if you're using something like simple linear regression, we do have to reshape it. Okay, does that make sense to people? Okay, so
Hi, Victor.
yeah.
So going back to the reshape code there, so you have an x as a data, and then you have inside the data you have -1 and 1. Oh, I am having a hard time understanding what it is doing there.
Yeah, so this is actually the shape. So if I actually check this out right here, this is the doc string, is that you pass in the array here, and then the next element I could put like new shape equals. So maybe that makes more sense. It's like new shape equals. This -1, 1, you're like, yeah, what's going on here? Basically, it's a kind of convenient way to basically say that -1's kind of like taking that 100 and putting that, saying like 100 will be here, comma 1. So explicitly making it from a one-dimensional array to a two-dimensional array. So this basically is like a nice shortcut versus me. I could have typed in 100 comma 1, which would be explicit, but you'll see in very common a lot of machine learning -1. And basically that's just a placeholder saying, hey, use what the number of data points that were in this array X and use that as that number. So it's just kind of a nice kind of quick way to reshape things. Does that make sense, Simon? Yeah. So it's just kind of like an explanation. Kind of like
you could also do like
mm-hmm.
X dot reshape and then call the reshape.
Yeah, you can do X dot reshape.
Yeah.
Yeah, you can do that way too. So you can do like -1.
And in this case, you do the same, the -1. Okay.
Yeah, I could do it like that. So again, this won't change anything if I go back to it, right? I could have also explicitly said 100, 101, and that would do the same thing. For the record, you could also do 50 comma 2, because then that would make two basically columns in there.
2 columns. Okay.
Yeah, so you see this a little bit different. But in this case, it's just saying all the data points should just be in its own separate row. So that's why I can do, in this case, -1, 1. Cool. Yeah, this was usually like, this might be a little more familiar if you see this, but you can do it with NumPy too. Okay, sound pretty good? Okay, minor detail just because we're doing linear regression. Typical, like for your guys' project, you probably won't have to do this just because there's more than one feature. Okay, so now that I have this, remember how we can do model equals linear regression. This is from Sklearn. I create this linear regression guy here. I could have done like, I guess if I was nicer, I could have done like this too. So I don't have to like chain it together. Say model equals linear regression, right? And then say model.fit. So I have this guy. Oops, maybe I'm wrong. Did I do something wrong here? Oh, I didn't reshape it again. There we go. Now I can fit this. All right, so now that's 101, right? Basically say, here are my features, here are my targets, go ahead and fit against this. In this, I'm not just doing this right now just because I'm showing for illustrative purposes. We probably would have like X train and Y train, not just X and Y. So we would separate the training data set from each other, okay? So let's visualize the results. So you can see here, this is the data, and you can guess linear regression, not very good, right? So this is kind of expected because since we looked at the data, we can see that data just isn't going to be a very great like line, right? So just kind of showing a little bit like how would we evaluate this? Like we can clearly visualize this, like, hey, this is no good. But the way you would do this, especially if you had multiple features, you say, okay, residuals are equal to my y hat, which is my prediction, minus y. Okay, so now I have residuals, and then I want to visualize those residuals. I can use something like displot or histogram or whatever. I like Seaborn's displot because then I can actually show the KDE. So remember, this right here is showing the residuals, right? It's showing how many residuals have, close to 0, and then you can see here as we get further out, basically these residuals are further away. So we can see most residuals in this case are about like somewhere around like 0 to 10-ish. Okay, does that make sense, people? And you can probably guess like, yeah, that makes sense because a lot of data points are pretty far away from the actual line. Okay, another way you can visualize this, I'm just showing Violin Plot, Swarm Plot. This is the same. This is showing the same exact data, but maybe it's a little bit more easier, a little bit easier for people to understand. And you can see here it's the same data again, but in this case, I can see the actual individual data points, and I can see in this case a Violin Plot. Okay, cool. So all sound good? You understand?
Okay, now I understand why the violent plot are used. Is it for that heteroscedasticity or something?
Yeah, so that's what we're going to end up looking at, is saying, hey, like, is this heteroscedastic, right? But that's what we're essentially right here, we're just bidding it together. And so I'm just kind of showing a little bit like how the what's it called? The data points, right? How the residuals like just are distributed from our data in our model. If that makes sense. Yeah. So we'll go into it now. It's like, okay, like how do we look at, like you said, Simon, heteroscedasticity, and then, or if it is heteroscedastic, which is what we don't want, if we want it to be homeoscedastic. And then we'll also look at, are the points normally distributed? So looking at this, like that's kind of what we're doing here. We're doing a little quick visual, like, is it, like the quick thing we say, is it normally distributed? What would you all say? Would you say this is normally distributed?
Is it partially normally distributed?
Might be close enough, right? It's not too drastic, right? Like it might be a little skewed left and right, but I don't think it looks too bad. And one way we can do this is just look at the histogram. One other way we can do it as well is actually using stats models. And then I can also use SciPy stats here in this case, which I think that's what I'm using. Yeah, so you can see here I'm using stats models in SciPy with stats and SM. So we can actually use this, and I think that's actually what the curriculum shows in the appendix of that linear regression. So I'm just importing this. We've seen this stats models in SciPy stats, and what this is going to be is going to use something called a QQ plot. So have we talked about, did we mention QQ plots, right, when we talked about checking normality? I think I showed like there's a histogram
Yeah.
and there's a QQ plot on the right.
Mhm.
So I'm sorry, someone have a question?
Yeah.
Mhm.
No, I said yeah.
Okay, yeah, okay. Thank you so much. All right, so you can see here, I'm just making a QQ plot, which is from stats models. And this is how you would call it to get that QQ plot. I'm passing the residuals. This dist equals stats.norm. This is basically just showing the normal distribution, like what a normal distribution should look like, which in the QQ plot is just a straight line. And then in this case, I'm just creating the line to 45 degrees, so that way it's a little easy for us to see along this diagonal, okay? And you can see here, it basically just takes those residuals and it's going to make our QQ plot for us. And you can see is that if it was perfectly normal, it would be perfectly on this red line. And in this case, you can kind of see, it's like, well, like you can imagine this like the CDF. So it's like, oh, like it's close, it's pretty close here, and on this top right, it might fall a little bit under, which you can kind of make sense. Like if you look at the histogram, it's like, oh yeah, it's a little bit maybe like a little bit higher than it should be. If it was normally distributed, we'd have a little less curve here. And then we'd expect a little more extreme values, but it looks like those extreme values are a little bit higher than it should be. You'd expect it to kind of fall off a little bit more. So you can see like, okay, it's normal. It's roughly normal. And again, this is a visual test. It's not a strict like, is it normal? It's like, it's normal enough. I'd probably say this is fine. Okay. Everyone see that? Especially when you compare it with like something like this, you can see it's roughly normal. Cool. All right. So then the next part is it homeoscedastic, right? So what we want here is we're getting our residuals, and all we're doing basically is plotting the residuals with the y hat, right? Y hat basically is what's it called? Like where our actual prediction is, and then saying how big those residuals are. And you can see in this case, is this homeoscedastic? Let me ask you another way. Is this good, the residuals, or is it bad residuals?
I think it's okay looking at that violin plot.
I think it's bad.
Yeah, I think we got some conflict here. I think I would agree with Chuck here in this case. It would actually show that it's not what we want. And the reason why we're saying this, there's definitely a pattern here. You can see there's a pattern of the residuals being relatively low, and then going relatively high, and then relatively low again. If it was homoscedastic, which is what we do want, it would be close to randomly distributed above and below. So in this case, this kind of makes sense because if we look at our data, right? Yeah, this wasn't a linear linear data, so we wouldn't expect our linear line to do a good job, and that's why we're getting, for example, really high residuals, when it's in this place, and then as we get further to the right here, we can see that they're a little bit low and then a little bit high again. So that's kind of what we're seeing here. Okay. Well, does that make sense to everyone? Cool. So in this case, I would probably say that, oh yes, our data are normal, right? Or at least our residuals from our linear regression line are normal. So we passed a normality test, but we did not pass, in this case, it was not homoscedastic. It looks like, there's some pattern there. And that makes sense because we know it's a quadratic data trying to be estimated with a linear regression. It's like, not going to quite work. So how do you fix this, right? Well, one, we just give up, right? So we're not going to just give up, right? So the next thing we do is actually check out some polynomial features. So like, hey, let's go and try to add some more complexity. Basically, this model's not doing a good job of actually performing really well. Let's check it out. And one way we can also do this too, which I didn't put in here. What was it called? Model, right? And we can actually check out the score. Oops. There we go. No, wait. Oh, we got to pass in the data for it. So you can see here is that on the model for these scores, like, that's our R-squared value. It's like, oh, you see, that's not good, right? 0.07, ooh, like that's pretty poor, right? So we can kind of see like, okay, it didn't do very well. So one way we can do is add new features. So I didn't show you all this. There's a few ways you could do this. One way that's a very straightforward way is basically just add a new feature, like if you had a data frame and add a new feature called, x squared, right? So you'd have, let's say we have feature 1x, and then we have a new feature called x squared, and you just do like x times x, and then have that into our new part of our column. A nice kind of convenient way is using Scikit-learn's API, is that we can actually import this polynomial features. And what this will actually do is that it will actually generate these polynomial features for us, so we don't have to do it ourselves. And in fact, it's kind of nice because you can also specify what kind of like what degree you want the polynomial. So you can actually choose, say, hey, I want to go up to, not just x1, x to the power of 1, x to the power of 2, but x to the power of 3 or higher. So that's what this is doing here. So this polynomial features, basically it's going to generate new features for us, which we'll call x poly. And we can pass it in saying, okay, degree equals 3. So basically what power we're raising it to. We can also pass in interaction only. By default, I think interaction only is false. But I just wanted to show this is that if we, for example, say, hey, we don't want polynomial features, but we want interaction terms, we can actually set interaction equals true. And that will only consider, like, let's say you have x1, x2, x3. We can do x1 and x2, x2 and x3, and so on. So you can basically do all those combinations for us, which is pretty convenient. But in this case, since we only have one feature, I just make sure to just put it to false because it's just going to be, that single feature to the power. Okay. And then this bias right here. So when you hear bias, when you're talking about linear regression, what we're talking about is a constant term. That's that beta 0, if you remember back when we were doing the equations like that. So this is just a constant term. So we're just including that in here. Okay. So once we have this basically defines, this doesn't change anything. This basically defines how you're going to change, what's it called? How you're going to like change the data. So in this case, we have poly features, and we do the way it works with Scikit-learn. If you have poly features, which is this guy, dot fit transform x. So x was our original data, and then basically it's going to pass in new data. Basically, it's going to take that new data and do a fit transform, kind of like when we did our scalar. Remember when we did scaling? It's doing the same thing, that fit transform. It takes in the data and then putting out new data. So this is where we get x poly. So x poly will actually have now not just one column, it will actually have 3 columns because it'll be x to the power of 1, x to the power of 2, x to the power of 3. Okay. So if we print this out now, that's what we'll see. Oh, I'm sorry, we also have the bias too. So it's x to the power, like you can imagine like x to the power of 0, or basically just a constant term. And so you can see here, this is our first data point. And this is basically, this is x right here, and this right here is x squared. This is x to the power of 3. Cool. Any questions on this? All right. So the main idea here is basically we're creating new data. We're transforming the data with these polynomial features. All right. So now we have these polynomial features. We can take that model and do linear regression again. So making a new linear regression model, and we can fit it with x poly and y. So y hasn't changed, right? But we're basically just using polynomial features. And then in this case, I'm just going to split this up so we can kind of look at it a little bit better. So I go ahead and fit this. We have our model. And then we can actually predict saying, hey, xpoly. Now, again, if you had this normally, like actually do a train test split, this would be the training data, and this would be the test data or a validation set. Okay, most likely a validation set since we're not done here. And so we make this prediction, and we can see, hey, not bad, much better, right? We can see in the red here, it's fitting a lot better to the data, which makes sense. And you can probably guess is that it's probably closely related to, if we look at the coefficients, my guess is that the x squared term is probably going to be a lot higher than the coefficient for the x cubed term. So we can also check that out too if we do model.coefficients. You can see here, yeah, there's definitely some value here. Looks like there's no really, the bias was like almost zero. That kind of makes sense because I didn't really do a really complex model here. And you can see the x cubed term, which is this guy right here, you can see it's relatively small compared to the other two, which makes sense. We don't need the x cubed term really to make a good prediction here. Okay. Makes sense? Cool. Any questions on this?
So if you did have a higher x cubed term, what would you see in the shape?
Yeah, so if you're familiar with like what x cubed looks like, you can imagine there can be up to 2 humps. So you can see for x squared, you get 1 hump, x cubed, you can get up to 2 humps. And then as you get more and more, that's kind of like how I remember this. It's from math. It's like literally like as you raise the power, you just add another hump that could be in your data. Technically speaking, this is a cubic function because this value is not 0. So it is keeping in like x cubed, but it's very, very small. So there's not much change from a normal quadratic equation. Good question. Cool. All right, so let's say, okay, this looks good, right? But let's actually evaluate and see how it does. So let's actually find the residuals for this new model, right? Y hat. Let's check out those residuals. So you can see, oh, like first of all, like I think the first thing you can say, hey, this looks a lot more normal than before, right? So you see the residuals hopefully are more or less kind of left above and below the linear regression line. Okay, so I can also do the violin plot. You see the data is relatively centered around here for relatively low residuals. And then I can also see the QQ plot, which looks like it lines pretty well. There's some extra, didn't do very well. You can kind of see right here. This value is a little bit lower, but that's okay. We don't expect that. And you can see the tails are relatively good, right? Maybe a little above, maybe a little below, but it's decent enough. Okay, so I would definitely say, yeah, pass the normality tests. Okay, now this is the one that we failed on, right? Is it homoscedastic? And in this case, yeah, it's homoscedastic. Like it's not perfect, right? Like, and that's the thing, it's a visual test, right? And basically the idea here is like it's roughly random above and below. And you can see maybe like right here, yeah, it's not doing the best job. Like, I mean, I don't know if the best job is the right way, but basically it's not randomly distributed above and below, but it's approximate. I think it does a pretty decent job. Okay. There's no there's no like really obvious pattern in this data. And maybe that's because I added a lot of noise. Maybe if we had more data points, we would get a better model. So that could be it too. Okay, cool. Sound pretty good? Any questions so far? Cool. So one thing you can consider is when you see how I'm kind of basically doing the same stuff for evaluation, you could potentially make some functions to kind of encompass a lot of this stuff together. So you don't have to rewrite all of this, literally copy and paste it. You could maybe, make a function that's going to output some of this, these graphs for you. So you don't have to like keep rewriting it over and over and over again. So that's something to consider that I didn't do here. Okay, so the next thing is like, well, polynomial degree 3 was pretty good. What about polynomial 12? Let's make this model like really work for it, right? So in this case, I have polynomial 12, which will now create, including the bias. Well, let's include the bias. I don't know, I put it false there. Let's include true. And now we have 13 different features, one of them being the bias. It's like, it's got to do well now, right? Let's see how it does. All right, like look at that squiggly line, right? Like it's definitely working really hard trying to get the prediction. Hopefully you hear my little bit of sarcasm. What's wrong with this? Like, why would I actually say this might not be a good idea?
Is this the over-predicting thing that you were talking about?
Yeah, so this is overfitting. So this is where in the curriculum, I don't know if I explicitly stated it, but variance versus bias. Basically, it's that if you add too much complexity to it, it's going to try to overfit. It's trying to be like really try to fit to each data point as best it can, But in reality, it's like you look at this data, you're like, you know what, this data looks like it's basically just a quadratic with some extra noise. I don't really know if like the true like model, the true like generator of this data really does look like this bumpy ride over here. So yeah, so in this case, I'm like, yeah, it looks like it's overfitting. It looks too complex for what the data actually are. Just to show you a little bit of evaluation again, what that looks like is that this would be your plot. So you can see it's like normality. Normality holds pretty well. Usually our data is pretty normal. You can see here again with the QQ plot. And then our residuals, you can see our residuals also homoscedastic. So you can see here is that this by itself, these assumptions do not tell you how well the model does by itself. What this is telling you is saying, hey, this linear regression and the way you defined it actually work for this data. Like, is it applicable to this data? Right, and that's essentially saying, yeah, you can use a 12-degree polynomial to predict this data, but this right here is telling us like, hey, this is looking overfitting. Okay, how would we like kind of question a little knowledge check here? How would we check to see if our data is overfitting on the training data? What could we do? Because I can see it, but like, how would I like actually observe this to confirm that, yeah, this is starting to overfit?
Maybe R square?
Say again?
R square?
R squared? So yeah, we can check out R squared, right? So what would we expect with R squared if it was overfitting?
It's close to 1. It's higher, right? Like if it is.
Yeah, so close to 1, higher value, and you can see, hey, that did really well. I don't think we checked that. You know what? I tell you what, I didn't even check the score for this one, did we? So let's just run this real quick just to make sure that what this score is. I guess I don't have to retrain it. Well, I did have to because the model is different. So let's go check model. It was X. Is it X poly? I called it right. Y. Okay, so it's like R squared of 0.58, and just to rerun. Okay, sorry, I'm making sure I'm going on the right things. That sounds messed up. Okay, so then we go to overfitting here, and we get our model score. So last one was 0.58. This one's 0.65, right? So it did better. It's not close to 1. So does that mean we're overfitting or we're not overfitting?
I don't think that number is really gonna tell you overfitting, because the higher you go, it's better, right? So I think we have to look at some other.
Yeah. So yeah, this by itself, the actual scoring on the training, like we trained it with XPoly, isn't going to tell us directly, at least, if it's overfitting. Like it might suggest, because we do want to get a better model, right? And this model objectively is doing better on predicting the data that we gave it. So that's the key part right here, is I'm kind of leading into. It's like, this is what I didn't do right here. I didn't have testing data. I didn't create any validation data. I didn't check data that's the model has never seen before. So this is the value of basically doing that train test split, is to make sure you have data that the model has never trained on. And then in that case, you might have new data points that's not going to perform that might not perform very well on this. And so if I want to let's say I just quickly create some training data here, or some test data. I'm actually going to go all the way back here so I can save this later on and send it around. Let's create some test data just for the heck of it. And we already know this is like the real way I created it, but I'm just going to create new random data. So note that this is going to create new random data, and I'm going to call this X test and Y test. Okay, you see how everyone see how this will create new data that I haven't seen before? Yeah. So just to show you all. Hello. Oh, question? No? Okay. All right, you can see here, like it's not super obvious, but you can see if you kind of quickly look at this data is different from this data. Like it's on the same pattern, right? Which is what we'd expect. But like it is going to be different from each other. So if I pass this X test and or Y test, I can see how well it performs. So let's see, this is the model score before, and let's do the model dot score And then remember, I have to transform my x with the, what did I call it? Poly features. So I have to do this guy here, but instead, I have to do a couple things on here. So one, I have to actually create, I'm gonna call it x test equals x dot reshape. Oops, x test dot reshape. Remember, I have to reshape it because we only have one feature. So I'm reshaping it there, x tests, and I'll call this x test poly. Okay. Everyone see what I'm doing here? Oh wait, I realized that's not right. Sorry. There we go. So I'm creating this new feature. The poly features has already been trained on saying, hey, like you transform it into the bias, and then x1, x to the power of 1, and then x to the power of 2. So if I do like x test here with poly, we should see, that's what we see. There's the bias, 1 term, 2 terms. Oh, I did it with 3 degrees, so 3 terms, right? It's like, okay, wait, that looks good. Now if I do model.score, which should be the same model up here, x test, y test. Oh, sorry, x test poly. You see, okay, like 60, like that actually did better than our training data, ironically enough, right? Actually did pretty well. So we got an R squared of 0.63, right? Just about there. Okay, let's do the same thing now though. After I close this guy, let's actually check it out with this overfitting data. So I have to rerun this because I called it model. Probably should have named it something else so that we wouldn't have to rerun it every time. But remember that model score should be about like 0.65, right? So then if I do, let's do the same thing. And I think everything is the same. X poly. I'm just, if you named it different things, you would change out this name, but since it's the same thing, I can do this. So this will be on the model that's trained with a degree of 12. If I do this model.score here, you can see it actually does not perform very well. In fact, if I look back on my test data, if I looked at my test data and say, hey, how well did it perform the test data that it never saw before? Remember, it never saw what X test was. We can see that the second model, which looks good, actually, like if you look at the score from the training, from that X original, it looks better. But we look at the actual performance on test data that's never seen before. You can see it actually performs worse than what we saw on the more simple model. So in this case, we say, hey, we're starting to overfit. Basically, we're getting more complexity on here, where basically the test data is no longer, the model's no longer generalizing well to data it's never seen before. Okay. Does that make sense to people? Give thumbs up if that made sense. Any questions? Like, I know that's a little subtle, but hopefully that makes some sense. Yeah. Okay, so this is the importance, again, why you should have training data and your test data, right? Your validation data. Another way we could have done this too is using cross-validation, right? So last time we have done something where we would do a cross-validation and you would see how well it performs. And that can give you a clue on saying, even if you only had, if you didn't have a test data, a holdout set, you can still use your training data and use, what's it called? Sorry, I'm losing my train of thought now. You're using your training data and using it in cross-validation, and that will give you an idea of how well the model will generalize. Okay, and then what you'll do for a project, like let's say for your phase 2 project. So this is kind of key point. So everyone who's like kind of falling asleep at the keyboard right now, I only say that because I can't see everyone's faces. Is that what you should do? So everyone tells me like, how should I do validation score? What you do, at the very, very beginning, you split off some of your data and you keep it off to the side, right? That's your holdout test. So like 10 to maybe 20% of your data, right? It's going to held out away from everything else. Then your training data, you're going to train your model all the way through with just your training data. And to see how well it performs, you're going to actually use cross-validation. Okay, so by using cross-validation, you can see how well it performs. And then once you feel confident in the model that it's like this model is pretty good, you're going to retrain it on all of your training data and then evaluate it on your holdout set. That like basically like once you like think of it like once you open up the package for the test, like the holdout test, and you train your like you predict on that X test, you should not be changing your model anymore. Does that make sense to people? So would you guys like to see a little bit like what that looks like? I didn't have it built into this, but that could help maybe if I showed you a little bit like, hypothetically speaking, if I had done this, what it would look like. Would you guys like to see that? Give me a thumbs up if you guys would. Okay, so let's try that. So let's go double check this. Scikit-learn. What was I saying? Cross-validation. So just to make sure that you have it right. So bring up the actual documentation and well, let's just scroll through here. So there we go. So this is what we want right here. So this is where, again, like I'm trying to show you a little bit like, you know, hey, if you can't remember what it is, that's how you search for it. So I'm just copying this part right here. And what we're going to do, so I'm going to put a little figure, cross-validation. So you can find it a little bit later. So, okay. So let's say do some cross-validation in here. And what we're going to do is, if you see right here, what this shows is that basically we're going to feed in, this is the model itself, and then the data, this is going to be the training data, and the cross-validation here is how many folds we have, right? So in this case, like 5 is usually pretty typical. So what we're doing here is this is going to be, and this is where I should have, I'm just going to rename it, guys. Everyone. I'm going to change model to overfit so I can like actually redo this every single time. Hopefully you all see what I'm doing here. I'm just making it so I can make it a little bit easier for me to redo this. And the xpoly, I'll call this overfit. The thing is like when you do this kind of stuff, you have to make sure that you name all the things the correct. Otherwise, I have to well, I should restart the kernel at this point, but hopefully everyone's seeing what I'm trying to do. Okay, so this was my test set stuff. So I'm going to comment this stuff out. Okay, so I'm going to redo this part right here. This should all work. Okay, good. So nothing's changed. That's what we want. Just get rid of that. Okay, so now I'm just passing in my model, which is the overfit model, right? And then my x is going to be the xpoly overfit, right? Y doesn't change because y was already what it is in CV. So if I do this now, we can see here, this is basically how well the model does. Now, remember, this is actually using the root mean squared error, right? So just kind of be aware of that, right? Is that like, this is not going to be the R squared value, but it's related, right? And in fact, I can probably just do like -1 times. So then I get not the negative root mean squared error, but the root mean squared error. Okay, everyone see what I did there? Like why I did that? Okay. So, okay, I have this is my score. And what I can look at, let's say overfit scores. So I'm just making that so it's a little easier. So we see overfit scores. And then what I want to check out, it's like, okay, let me see, for example, what is overfit scores dot mean, right? So that's the mean. And then the standard deviation, overfit scores dot standard deviation. Okay. So we can see here, like these are the values that like it fluctuates through, right? It's like, okay, like that's what my scores were for this overfit XY. So you can see that it doesn't do a great job from here, but what we want to really compare it to is our original data, like not original, but the other model. That's what we want to really check out, because this means nothing for us without comparing it to another model. So now what I'm going to do, I have to rerun this guy just because, be a little careful. Okay, so this would normally be done right after, right after I had done this model and produced, this cross-validation. But since we're kind of like skipping a little bit around, and then this case is just model, and this should just be xpoly, I believe. Okay, and then y is the same. Okay, and then let's just see what overfit scores are. Oh, I shouldn't call it overfit score, should I? I should call it I'll call it like scores. So this is a different model. So everyone see what I'm doing here? Like this right here is fitting for a different model for that overfitting model. And this one is using that simple model that I just ran a second ago. Okay. And so then if I do this, go ahead and check out those scores. And you can already see, like just quickly looking at this, like what can you already see? Like these values, some of these are really good. Like you're like, oh wow, like, you know, like 0.8, you know, 0.17. But some of these, holy geez, like this is in the thousands, right? Like this is a huge variance, and you can see that on here. But looking at these scores, you can see already, like these are relatively small and pretty close. And so if I do the scores here, you can actually see, this is where I have the little drum roll going on. See, hey, the scores are like pretty small here. And this right here. So this is again, like we want a small root mean squared error, right? So this is a better model on the data. In this case, I never use the test data. Like remember, I never even looked at the test data in this case. Like I didn't apply this at all. So you can already see is that even without looking at the test data, right, which is kind of like, you got to be careful like using at the very end because you're basically start overfitting on it. This is telling you saying, hey, my data or my model is performing much better here than over here. And we did just cross validation with that. Excuse me. That makes sense to people? Give me thumbs if that makes sense. Thumbs up, thumb sideways, downwards if you're like, ooh, I don't know. Okay, see some thumbs up. Any questions? Yeah, this is where if I'm like a little careful, right? I could put something like, this should be like basic model.
Hey, are you going to update this notebook on your?
I think I should, right? I actually haven't
Yeah.
uploaded this yet, so
Okay, awesome.
this might be something I might need to update a bit before. And this is where like you can see like when I'm doing things live, like this is why you should comment your code, because otherwise you can look back on this like, what was I doing? And you can see a little bit like, that's why it's a good idea. So this is actually a good example of like how you might structure like when you're doing stuff. You should like, I like to give people advice saying every like 30 minutes, like literally every 30 minutes, maybe an hour at the most, pause, don't do anything, and just like literally go kernel restart and run all, and then restructure, like, you know, move things around as needed. Just basically cleaning it up. And I think that's easier to deal with versus you working for like 5 hours, you know, like you're on a computer, you're typing away, you're doing all this stuff. And then you're like, oh, good, that was a good session. I got some good feels in there. You save it, come back, you know, 2 hours later, and it doesn't work anymore. Which, trust me, happens quite a lot if you're used to that process. So it's a good idea to kind of take a little break and like, oh, let me take some time to structure. And I say literally like set a timer if you like have to. It's like every 30 minutes, every hour, just restructure things. And I think that helps people not come with issues and stuff. But yeah, let me make sure while I'm doing this right here, since I have this. Oh, this is for the, see, I already lost my train of thought here. So let's see, overfit model. I wish that wasn't a misspelling, but that's how it's spelled. All right, so kind of speaking back to like, okay, like make sure things work. Let's do a kernel restart. I'm gonna clear output too. And then what I'm gonna do, in this case, I have some stuff under here that we haven't seen. Let me just do cell run all above. And then if I have an error, it won't hit there. See, we have an error here. So something happened here. That's where I have to be a little careful, right? So this is when we were starting to overfit. And I did something here, which is the value error. It's y hat model. So it's right here. So hopefully you guys don't mind me actually showing you a little bit like what happens when you hit these errors and stuff like this. But let's see here. I think what's happening is that I'm passing in values. You see the size 4 is different. So this should be x polyfit, transform x, poly features. So this should work here. We can see that works here. X poly overfit. Oh, see, this is why I think this little x right here, this little x, I believe should be this guy. I think that's right. No, this x should be here. See, if you're never sure, oh, this should be y, right? No, sorry, I'm trying to think through in my head right now. So, does anyone see what's going on here?
Should it be y hat overfit?
Y hat. let's see here. So I predict it with y, right? Yeah, no, I don't see exactly what's going on here, to be honest. You're saying this should be, I should rename this. See, this is my error right here. And
Yeah.
it looks like, oh, there it is. Model overfit. Everyone see that? So I think from there, okay, and then doing this, cool. See, this is how you address errors, right? And this is why you should like name things like, ideally you should name them different every time you use something new. Otherwise you get this stuff, weird stuff. And this is why also you shouldn't, like ideally you should have a function, right? And that way you can just pass in the model and like have it do things versus copying and pasting, because then you might copy and paste the wrong thing. Okay, so we can see here, cool. Technically got a little higher score. Exciting. All right. Okay, just to make sure I have everything running here, I'm just going to keep going through. Overfit scores was not defined because I somehow moved it up there. There we go. Okay, I think we're back in business now. And I'll fix that later. But hopefully you also see now a little bit like what that looks like when you get in a weird spot, right? That's why it's also good to do that kernel restart and redoing it. Okay, so we have about 15 more minutes left too, so I'm going to show you a couple things. So one thing with missing data, you should explore your missing data, right, and figure out what are you going to do with it. Like if there's some values that are missing in one of the features, you actually want to like say, okay, like what do I do with this? What makes the most sense? You investigate it, and then you say, you know what makes sense? I'm going to replace it with the mean, right, or whatever it is. You know, I'm going to replace it with the median. In fact, I'm going to change the median because I like the median better. Okay, all right. So you're like, okay, cool. Then how do you actually build this? It's like, well, you could have a function like I showed before. You can write a function and that says, all right, take in the training data, take in the data that you want to change, right? Could be the X test, for example, or whatever it is, and then change that. The problem is that if you do that, it ends up being hard to do cross-validation score, because now what happens if you have a new data that comes in, you got to figure out how to replace that data and all that stuff, and it can be kind of weird. And because if you think about it this way, is that if you do cross-validation, right, but you replaced all of the training data with the median, when you do that validation, that little fold that's going to be your validation set already knows a little bit that the overall median is this value, so it's already kind of incorporated. So really what you should do, this is hopefully, it's a little subtle, but hopefully it's making sense, is that you should instead redo all of like this, like the 4 folds. That's your new training, and then your cross-validation little validation score or validation set. You say, okay, like fit the median for this training set, and then apply it to your validation set in that one instance. And that would be more accurate of saying, is it generalizable? Okay, does that make sense to people? Yeah, kind of. So basically what I'm trying to say here is that the hard part is actually building a function that will do that for us. Well, it turns out Sklearn, since it has that cross-validation, actually has something called an imputer. And this imputer basically can take, you know, for example, I've had this missing data here. You can imagine these are data points, like, you know, 5 data points here with 3 columns, right? And there's some missing data, right? What I can do is say, hey, take that missing data with this simple imputer and replace that with the median values. So again, what this is saying is like, hey, take a simple imputer, and this strategy is just replace it with median values. And the way you fit it, you can actually just do fit like this, but you could do fit transform too. So you do fit, is okay, like this is going to fit, I'm just going to do this one by one. This fit like this, okay? And what happens now is that this imputer now knows, like, okay, it knows now, whenever I see a missing value and you use me, I will use the median from this data specifically. So now if I have the data, let's say I'm just gonna use X missing again. So I do imp.transform X missing. You'll see now it's replacing the missing with the median on this column, right? And the median in this case looks like it's 6, right? And the median over here should be like 4, 3.5. Okay. Everyone see that?
So this function knows to divide by columns, and it doesn't just put all the values from the entire array.
That's right.
into
Yeah,
one
it actually
pool.
knows
Okay.
look at each column and look at, you know, whatever the strategy is. In this case, the strategy is median. If I put mean, you can see a little bit how that will change. You can see here in this case, this went 4.5 instead of 3, or whatever. Okay. Does that make sense to people? So now it's like, okay, like that's cool, Victor, but that seems like is that really any better than what we had before? The cool part now is, now let's say we have some new missing data. So let's say we have np.nan here, and I'm gonna call this x new missing. Okay, and now that's where I'm getting rid of my nice formatting here, which I copied for the record. So you can see here what the mean here is just 1, right? So like if I were to refit this, it would just replace it with 1, but that's not what I want. I want to replace it with, in this case, 4.5, what that actual mean was supposed to be, right? So now if I go ahead and write this guy, say, okay, have my x missing new, I do imp.transform x new missing. This is going to replace now those missing values, not with the mean from my data I fed it in. I'm just transforming it from what it's already been fitted with, x missing. So now it's fitting it with 4.5. Everyone see that? So again, this allows you to say, only use the training data that I fed you to determine what to do with the new data that you've never seen before, versus like trying to retrain it. Okay. Does that make sense to people? Give me a thumbs up if that makes sense. Thumbs down, you're like, oh, I'm still lost. Okay. All right. Any questions? Okay. So for the record, you probably could create this function, like something like this, which is what I basically did last time. But this is a little more extensible, where you can kind of like decide. And in fact, you can even decide certain features to do certain different things. So you can actually look into that too, if you look at the documentation for Simple Imputer. But that's the idea here. Okay. So what this all leads up to is something called pipelines. So this is something I didn't show, and this is technically not until phase 3. So just kind of know is that like I'm technically showing you something that's like not in the curriculum directly, but you will see it. And I think it's important enough where I'm like, I want to show it to you all. Okay. So we have these different steps. You can kind of imagine like what are the steps that we would actually do in taking this data and changing it. Well, first thing is like, you know, we want to make sure we take all the data and replace the missing values. Like, okay. And then we found out, you know, polynomial features are actually really great. So it's like, okay, we'd want to then apply polynomial features. You know, in this case, we found out degree 2 is actually really, really useful. It's like, okay, like we want that part. And then finally, we actually want to train the model, the linear regression model, and do that. It's like, okay, like you can imagine now, step 1, like if I wrote this from scratch, ignore this for right now, but like if you wrote this from scratch, you would have to write a function that basically applies the finds the missing values, applies, you know, whatever strategy you have. And then the next part being like, okay, now I need to, what's it called? I need to find polynomial features, so then transform the data to get polynomial features, and then finally feed that into your model.fit for linear regression. So that can take a lot of steps, and it's really easy to accidentally make a mistake, right? So Sklearn has something called a pipeline. And pipelines are a very general thing in data science, but Sklearn's API, I think, is really good with this pipelines, is that basically you can create the model. Remember how we did the model.fit? That would usually be model equals linear regression. Well, what you can do is actually make this pipeline object right here. And basically what's going to happen is that when you feed in data, remember when we do that .fit? When we feed in data, what's actually going to happen is that it's going to take the data and pass it into Simple Imputer. So it's as if that Simple Imputer has already been trained up, right? And then we say, okay, then go ahead and apply the polynomial features degree 2, okay? And then go ahead and fit it with linear regression, okay? So what's nice is that I don't have to rewrite all these things, is that as I discover like what's the best way, I can just create this object, you know, my pipeline. Sometimes you might even call it pipeline versus model. So I can just add this in here, and that's kind of going back a little bit, like saying how you can always edit stuff, you know, to make it more presentable, is that you're discovering things, and as you discover it, you have at the bottom of your like notebook this pipeline object. You just keep adding stuff to the pipeline as you make changes and stuff to match what you've discovered. And what ends up being is this really neat, you know, little object here. So I can run this guy, and then I think X is fine. Yeah. So I have X here. Remember, X is the pure data. So just kind of reviewing a little bit just to make sure I got the right data here. Yeah. So you saw X is this values here. Let's do plot that scatter real quick. Okay, that's our data, right? So now what we can do is say, okay, go ahead and fit with this pipeline here. Okay. And it's going to basically fit with everything saying, okay, use the training data to do simple imputer if there's missing values using the median. Use the polynomial features degree 2, and then do actual fitting on the model. So I can run this guy. Boom, my model's fit. And now I can actually predict then on top of this. In this case, I could do something like X test. I don't think I have defined X test yet here, but you can see like I have X test here, and then I have Y hat. So then I actually perform this part. So what's kind of nice is that I don't have to worry about passing in like accidentally training on top of like my new data that I've never had before. This kind of makes it nice and easy because now this dot predict will only use the new data to predict, won't use it to retrain or readjust the model. And I encompass everything that I'm going to change in this pipeline. Okay. Does that make sense to people? Okay. Thumbs up if that makes sense. Sideways, you're like, I don't know. Thumbs down if you completely lost. You see some sideways. So how could I help maybe in understanding, helping people understand this a little bit more? Because what's the most confusing part of it? If you guys are okay with the share. Yeah, so maybe it helps if I show a little bit, like if you didn't use a pipeline, what would that mean? What does that look like? Well, what I have to do for this same exact process, so say like, you know, this is kind of like with a pipeline. It's going to be without pipeline. Okay, so I got this nice thing here. Okay, without a pipeline, the first step I have to do is like, okay, like remove missing values. And then I have to do, or not remove, let's say replace missing values. Next thing I have to do is like, you know, create polynomial features. Degree equals 2. And then train model. Okay, so to replace missing features, I would use something like the imputer here. So let's say I get it like my imputer equals simple imputer. Oops. And then say strategy equals median. Okay, and then I would say, okay, I have to train that imputer, my imputer dot train, or sorry, not train, sorry, dot fit X. This is the data that I care about, right? So like, okay, do that part. And then I'd have to do this part, which is going to be create polynomial features. So I have to create new polynomial features. So I can say poly features, or I'll call it my poly features. My poly features equals polynomial features, degree equals 2. I'm going to say include bias. I see equals 2, or equals true. Okay, so we have this part, and then say, okay, once I have that, I have to actually fit it. So I get my poly features dot fit, and that's going to be of X, right? And then I'm going to call fit transform because I have to transform X as well. So then I say, okay, you know, this should be X. Oh, you see, in this, I already made a mistake. My imputer dot fit, I actually want to transform X too. So, oh, I have to do fit transform. And then I have to say, okay, like X, no missing, right? And then I got to pass this X part. It's like, well, X no missing should be in here for my polynomial. It's like, okay. And then I have to say X poly, I'm gonna say no missing. I'm being extra like redundant here just to make sure that I don't mess up. It's like, okay, X no missing here. That'll transform here. This is fit. Okay, and now I can say, okay, model, let's call it my model. Model equals linear regression, right? and then I say my model dot fit, right? And this is going to be X no missing, and then Y. Okay, so that's how I would. Does that make sense to everyone? Like this process I just did here. So you can already see like one of the reasons why this is kind of not ideal is because I have to write a whole bunch. Like, and you can see how easy it is to accidentally write the wrong thing in here. You know, like for example, if I use X instead of X no missing, that would change, you know, what's going on here, I have to debug and all that stuff. So it's more stuff for me to write. And then if I actually want to make a prediction, I have to do like my model dot predict, you know, in this case, I'm just going to use X, right? So that would make my predictions, right, of my new guy would be like y hat equals. Okay, that makes sense to people, like this whole part. And if I run this now, this should work. Oh, it looks like I messed something up here. Simple computer has no object fit transform. Transform. Oh, it should just be, wait.
Has to be dot, right? Feed dot transform.
Oh, I spelled it wrong. Transform. There we go. I forgot the F. See? Little mistakes like that. But like those are minor mistakes. But I could easily, like, you see how I just did that? Like, let's just say, oops. I have to check that later. But trust me, that's the idea that you would have here. Oh, you know why I have to do it this way too? So you see like what just happened? I tried doing my model.predict. Why did this fail when I ran this? Because X, like assuming, like putting X as new data, it hasn't been imputed. It hasn't done polynomial features. So I got to actually transform. It's like, oh, you know, now I have to say transform new, I'll call it like new data. Okay, so I got to do something like, you know, like, oh, X dot predict. I'll say like, you know, X new is equal to, I got to do my imputer dot transform X, and then I got to do X new equals my poly dot transform X. Okay, and then I can pass in X new here. Okay, do you guys all see that? So like this is now, it's like, okay, now X new is now in the same form that would be ready for my model to process. And now I get these values. So, and this is actually already wrong. Do you guys see what I did wrong right here? It worked, but there's actually something wrong here. And the fact that you guys had to take that second, right, it's not a good sign, right? Because like this could easily be something. So what I did here is I did X new is equal to my transformed X, but then I did my poly features. I just passed an X. I really should be passing X new, right? Because I transformed it once, and then I should transform it over here. And you can imagine that's a relatively small thing because there's no missing data. But if I had a bunch of more complex transformations for my data, this could be really bad news, right? I actually just made a mistake and I completely skipped, you know, this process. So, you know, now if I run this, will be, you know, this will be like following the same procedure, but I got to make sure I also do the right transformations here in this, and like in the same order. There's a whole bunch of ways this can subtly go wrong. When you do it this way, you can see all this code right here, and you can imagine you have many, many transformations, but all this code is encapsulated in here. And all I have to do is model.x, the original data, and y, and then I can do the predict with just the normal x. I don't have to do any transformations. I think, do I have x test defined? Let's see if I do have x test defined. So if I do, okay, so I have x test here. Remember, this x test is new data that's not transformed yet at all. I can just do x test. No problem at all. That was really easy. But if I did x test right here, if I just put us in x test, ooh, I got to change it, right? So I got to make sure I have, you know, x test here, and then we call it x new, and then x new is here, and then perform it. Oh, that didn't work either. So like you have to check, like you can see a little bit like how this can be a little frustrating, like trying to make sure this all works together. Oh, you see, I have x test. This would be x new. Okay. So you can see like there's a little bit more error for you to be able to, versus this one, if I get rid of this scatter plot, you can see here, it's relatively like there's defining this thing, as long as you define this one, dot fit, dot predict, done. Over here, I got to make sure I transfer the data in the right way and not leave out any steps, which on the best case scenario, I get an error and have to figure out why there was an error and work back. The worst case scenario is actually if I don't realize there's an error and do something like that, because then that will run, but it's not actually, skipping this step. So it's a semantic error versus a syntax error. Okay, does that make sense to people better?
So the pipeline can also contain your own function, right? The function that you define by yourself, or
You
usually
can
we just
define your own functions. It's a little more subtle. We haven't talked about object-oriented programming, which would be saved for phase 3. You can define your own functions to be put in here, actually relatively easy, but it relies on us doing OOP or object-oriented programming, which I know not everyone here has that. If you're curious on doing this, definitely ask me, but one of the things you can just look up is Sklearn Estimator. So you can do Sklearn Estimator. That's how you can create your own estimator. And basically, all you have to do in a lot of ways is essentially define two main functions, which is how is it going to do a dot fit and how is it going to do a transform. And then once you have those two, sklearn goes, okay, I totally understand what you're talking about. And, it will do that. You can then pass into your pipeline. But I'm not showing that here today just because you guys will see it hopefully for my phase 3. But it relies on us knowing how object-oriented programming works. So, but to go back a little bit, answer your question, yes, you can do your own functions. You just got to make it in a very specific way. Okay. Cool. Yeah, again, this is really useful. And again, one of the really useful things on this too is that I could have also done cross-validation score. So I pass in my model. Because remember, I can pass in this model here, and I can actually use, whatever data I have. And what's cool about that is that this will actually use this process here to make sure to kind of described is that it's going to retrain the simple computer for that fake, like four folds here, to do that, to get that median, and then apply it to like its validation data set. So it's not leaking out into that validation set, which is a little subtle, but that it's more truthful to like its actual performance on what you're trying to achieve from cross-validation score. Okay, cool. All right, I know we're kind of at time and everything, but how are we feeling on that? Does that make sense? Okay, any questions at all? I know this is like a big thing that's not in the curriculum material, but I think I think it can be pretty actually pretty useful. At worst, if you don't do this, it just means you have to do something like this, and you just got to be very careful, making sure you're not skipping steps and making sure you document and make sure you do what you're supposed to. Because as you all saw, this can be very easily, you can do the wrong thing. Cool. All right, sound good? All right. So I'll stop the recording here now, and then we'll have office hours after.